All right, guys, let's get started. All right, guys, let's get started. All right, so we are currently on week 7, I think. All right, so this is week 7. We finished the first exam. I've graded your exam, so you can check the grades. If you have any issues, let me know. So let me start the. So we are currently recording. Audio's on. All right. First thing. So today we're gonna start a new topic, a new sequence of topics. So the way that I've divided the semester roughly, like 3 areas, roughly. I mean, they're not precise, but so the first time, so let me see. Let me share this. So the first area that we did was basically a lot of the vector space model ideas, right? So we explored in particular, see, these are, dimensional kinds of things. This is sometimes referred to as the rank of a matrix, right? So rank-based spaces, right? And rank spaces. And we looked at algorithms like KNN, right? And we also looked at techniques like singular value decomposition, okay? So the first thing I'm going to talk about today when I get into the topics is just the homework, right? So the code is now, so I fixed up the little bug I had last Wednesday. So I've checked the code. You can just use it, but you have to use it with a different data set. That's the only requirement. Okay. Actually, what's your name? Noah? You're Noah Ford? Yeah, so Noah, at the end of class on Wednesday, we were having a discussion about the results, actually. So remind me to talk about that, because it's actually a very good observation that he made, right? And so we'll think about it a little bit more. So actually, the homework, the way that I'm going to structure it is like 2 things, but it's still the same code. So the code is, it's already on Brightspace. But anyway, or on GitHub. So anyway, I talked about KNN, I talked about singular value decomposition. And certainly this is not going to go away. Vector space models are not going to go away. They're actually central to machine learning, right? It's one of the areas. However, we are about to start today a second approach to machine learning, which is the probabilistic approach, okay? So the probabilities approach, right? Now this, if you remember, you would, to create a vector space, you would order your data as X and Y, right? And we understood, we spent a lot of time on X and Y, and that's not going to change, okay? So that we're still going to format our data like this. It's just that now the assumptions are not going to be like putting points in a vector space and measuring distance, right? But instead, we're going to calculate probabilities, okay? So it's going to be a little bit different. So I'll start with that framework today. You've actually already used one of the algorithms that's probabilistic, which is called naive Bayes. Okay, so you've used naive Bayes already. And today I'm just going to go over, I'm going to start with the framework of it, which is an algorithm that is probabilistic in nature, okay? This is going to lead into something called the hidden Markov model, HMMs. And these are actually really interesting. They're also sequential, right? And they're pretty important. And so we'll talk about these. They're kind of built on the same ideas, probabilistic ideas. And there are other algorithms out there that are also built on, they all share ideas here and there. After this, we'll go into reinforcement learning, which is actually pretty interesting if you're interested in video games and things like that. you'll see what, this is extremely powerful. I believe true AI, might come from there if it ever does come anywhere. But anyway, this sequence of topics that we're going to look at, it's basically sequential, right? So we're going to take a look at it. Now, that being said, that doesn't mean that a lot of the ideas from here could not translate, right? They can't. And you can, in fact, because the data is still formatted like this, right? The data is still formatted like this, you could still manipulate it. Remember that in terms of singular value decomposition, we looked at recommender systems, and we also looked at compression. And compression, I explained last week, was basically we create a new set of vectors, but now we just select a few of the columns, right? And basically the information is captured in the first columns and not, let's say, towards the end. And so you lose some information, but you reduce the dimensionality. Okay. Any questions about that idea? All right, we went over that last week. So today I'm not going to cover singular value decomposition anymore, except to point out the code. So I loaded the Jupyter notebook, the updated Jupyter notebook on GitHub. So you can just use that one. I've gone through it. So hopefully all the bugs are out and it should be correct. So we'll talk about that. And then, as I said, probabilistic methods are these. And then really the last part of how I do the semester, once we're done with these methods, sometime a little after spring break, we will do neural networks. Okay, so you've probably heard of neural networks, right? And that will be the rest of the semester. Okay, that's ultimately the most powerful. Naive Bayes, from the point of view of like being a traditional algorithm, is pretty good, right? But as you have seen, it's basically the baseline, right? And what that means is that it is the we'll see today again, but it's fast, but the accuracy wasn't that great, right? It wasn't always your best algorithm, so that's an important thing. Okay. All right, so yeah, and so that's basically the plan. So today we're just going to focus on naive Bayes and probabilistic theory. It's actually very straightforward. I think you'll find it's less of a stretch. I think with singular value decomposition, you kind of just have to trust. Yeah, linear algebra says this. Trust me, right? And you'd need a lot of go to linear algebra and prove those theorems. Probabilistic methods are actually, they're more intuitive in a sense, right? And so we'll take a look at it. Hopefully it'll make sense. We're calculating the probability. Now we want to find a probability distribution. So we want to know for a feature, what is the probability that this feature came from this distribution? You see that? That's going to be the ultimate question, right? How likely is this feature in terms, I see a feature, you measure height, right? And somebody's 6'4", right? So what's the probability that that person that's 6'4", just for that one feature, what's the probability that they belong to the human, normal distribution, right? So most people are not 6'4", at least not here, but in basketball, right? That's so you know what I'm saying, guys? Does that make sense? So we'll take a look at those ideas, but they should be pretty intuitive. So at the end of the day, we're trying to calculate some probability for the feature somehow. And there's a couple of ways. We can just count, right? And just do it that way. Count, what's the probability that it's going to snow 2 weeks from now? You don't know, right? But look at February and January, count the days that it snowed versus the days that all the days, you got a probability. Do you see what I'm saying? So that's a simple one too. Okay, so that's what we're going to do. So first things first, let's go over the homework assignment. So this is assigned now, and I want you guys to work on it, but I will give you time. So let me share the screen. Okay, so let's go to the calendar quickly. So we are currently on this week, today's February 21st. So I'm going to give you 3 weeks, basically. So until March 9th to submit the recommender system. Okay. I'm giving you 3 weeks because I want you to do a good job. We're going to do demos on that day. You know what I mean? And you'll recommend something to your friends, to someone, right? So somebody should go in and put in a few things that they like and then make a few recommendations. So that part of the code I didn't give, right? So you'll have to kind of figure it out. But the rest of the code is already there. So I'm going to go over here to, let's go to the GitHub. And so if you go to singular value decomposition, go to recommender, and just click on this one, basic singular value decomposition recommender system. Okay. So here's the Jupyter notebook. So this is the code that you should use, right? So this is the code that you should use. So, you know, we got the libraries, you know, got the data. So remember how we read in the data. You may find your data in a different format. What matters is the final format that you should put it in, correct? That matrix, because you need an A matrix that you can decompose into the S, right? V and D parameters or matrices. Okay, so remember you can, you know, look at data like this. We talked about all of this, creating the dictionaries if it's too big, right? How to make it smaller, the dimensions. Then create the matrix itself. It's simple to get the singular value decomposition. And then I have a couple of ways of calculating the similarity, right? So we have arc sort. We have a NP dot over here, right? And we have the sklearn approach. So I just commented out the sklearn when I was doing the testing, but you can just use either one, right? Either one. And you can find other functions as well, right? So that you can find other functions. You could also try the Euclidean distance. Why not? It should work, right? And so test it out basically. And then here, you know, here's an example. I selected 200 principal components instead of the 610, and then you select a movie ID. You need to get the reference ID. Then you slice the matrix, right? Based on the dimensions that you're mapping it, you calculate the similarities, right? So these are the most similar ones, right? Remember? And then after that, all you have to do is convert these IDs, which are the reference IDs, into the real IDs, and then from the real IDs, find the actual products. Do you guys understand? So if you see here, these are the movies that it recommended. So for the movie Inception, it recommended Borat. It recommended Seven, Pulp Fiction, The Simpsons, Lock, Stock, and Two Smoking Barrels, Galaxy Quest, Star Wars, Shrek, Bruce Almighty, and Trainspotting. Now, we would have expected for Inception to maybe just do Leonardo DiCaprio movies, right? Or just do like sci-fi. However, Noah, you wanna you wanna say your theory? You had a nice point actually that I liked what Noah said. So go ahead. Yeah. Yeah, so that's actually a pretty good idea. So that's actually better than what I was saying, right? Because I was actually expecting sci-fi movies here, but really sci-fi movies should be represented in the principal component of sci-fi movies, right? So really, if we wanted to test just getting sci-fi movies, maybe the idea would be find the principal component that is sci-fi, which we don't know which one it is, and then select, let's say, all the ones that are like positive or highly positive. See if all those movies come out as sci-fi. Do you guys see that? And that might be a better way of finding sci-fi movies. Here, as you said, because there's 200 principal components, sci-fi, comedy, you know, Inception might actually be a sci-fi and what? Sci-fi and action. You know, it's like sci-fi realistic kind of thing, right? So maybe other ones would be like The Matrix, movies that are sci-fi and realistic versus. So I don't know. At the end of the day, can you not do that? We're in a class. Did you send something to print? We're in a class. You've been here before, and I let you in here because I thought you were just going to be quiet, but you've interrupted the class. You see that? I mean, we're in a classroom teaching a class, right? All right. So anyway, these are the movies. So you have one movie, and then you recommend the other. So what I would say is, as part of the homework, take a look at this one, right? Take a look at this, play with it a little bit. Maybe try out different movies. That's actually what I would do. If I was built, don't think of it as I'm going to build something for the homework, right? Don't think of it that way. Think of it as I want to actually build a recommender system. You see, I have 3 weeks for this assignment. I'm going to build a recommender system. So what are the things that I would do? First of all, I would play with a whole bunch of movies, right? To see if it's actually, showing something, right? That would be the first thing. The second thing I would do is I would, if the results are not great, for instance, if the results are not great, I would say that the problem is somewhere here, right? Maybe this is not appropriate. Maybe this is not appropriate. So maybe at a third, function, the Euclidean distance, maybe that one will work, right? But if I was doing this kind of work, this is where I would focus my attention on, okay? And just figuring this out, because this is really going to influence the outcome. Got it? And then once you've done that, so basically this would be like the tuning of this, right? So you're gonna like run experiments on this and get a feel for it. Maybe try Euclidean, see if you find one that convinces you. And then after that, you feel that the system works. Now find a new data set. Recommend something else. It could be anything. It could be shoes. It could be, whatever, cars, whatever. But please find the data set. You have to do this. This is on your own, right? So you can you can select this to be as difficult or as easy as you want it to be. The only requirement for me is it can't be the movies. It's got to be another type of recommendation. And you guys have to do the manipulating of the data so that it fits this. I would recommend make your data look like the movie lens data ended up looking, and then you should be fine. Does that make sense? Does the homework make sense? Are there any questions about it? No questions? All clear? All right, great. So perfect. So yeah, so that's please go ahead and do that. This is the code, as I said, it's working. I've tested it. So it should be fine. All right, the next thing we're gonna do is, let's stop sharing here. Okay, so now now we're going to start the new topic. Okay, so we're going to start our new topic. So you should all be seeing the whiteboard. Okay. And all of this, by the way, is already, these slides and everything is already on Brightspace. Okay, so you can just follow along if you'd like. Over there. So as I said, we are going to look at naive Bayes, because we're actually looking at probabilistic methods, right? But we're going to start with naive Bayes. It's actually very, probability theory in statistics is an actual course. Okay? So if you guys, were interested in statistics, you could take a course called probability theory, probably probability theory 1, probability theory 2. Right. So it's quite involved, but it's extremely important. All right. So as we've established, the naive Bayes algorithm is one of the traditional algorithms like KNN. in this course, because this is a machine learning foundations course, right? We're looking at the big things like vector space, probability, neural networks, right? Those are the big things. A lot of those techniques are traditional in the sense that they've been around for the longest time. Naive Bayes is not the greatest, but it's a good one. We'll cover, when we cover neural networks, we'll use deep learning. We'll look a little bit at that. So you should be able to, at least by the end of the class, be able to use it for some classification. So yeah, so naive Bayes is certainly one of the traditional algorithms, but it's simple and it should be clear to understand. You've already used it in Weka, but now we're going to write it up in code in Python so that we can see how it works, basically, the underlying code, and it's not too bad. All the code is on GitHub. So basically, what are some of the aspects of naive Bayes? It is fast, as you have seen. It is very simple, actually. It's a simple framework, simple enough anyway. And we're still doing this for supervised learning. So we're still using supervised learning. And we still have samples, features, classes, right? So we still have all of those. So for instance, here, if we just take one row, it could be, x1, x2, x3, ... xn, and then the class is going to be whatever we want it to be. So for instance, if we're using the iris data set, it would be 0, 1, and 2, which basically represents Setosa, Virginica, Versicolor, right? The three classes. So these are, as I said, this is a probabilistic approach. Okay. These are probabilistic approach. So here, okay, so here every feature gets a say in determining which label should be assigned by the classifier. Okay, so basically, to select a label, you have to select a label from the available labels, but you have to look at every feature. Okay, every feature has a say in it, right? So we have to find a way to basically associate a probability with each feature. So let's say I would say 0.5, 0.3, 0.2, 0.3, right? And that's for class 1. Then for class 2, 0.5, 0.2, 0.1, 0.2. You see that? And then based on these values, we're going to compute a final value, and we pick the highest somehow, right? Somehow so far. We have to figure that out. But the key thing is, for every feature, we calculate the probabilities. So, what would this be? Well, if these were, a specific, let's say, likes to play basketball. That's a feature, right? Versus likes to play soccer, right? That's a feature. So then you look at the probability that that action, likes to play basketball, is associated with class 1 versus class 2. You see that? So you have, it's a count. It's a type of a count of how many times in the data did you see people that like to play basketball and were associated with this class, versus the number of times that you saw people that like to play soccer and they were associated with the other class. Do you see that? That basically boils down to a count or a probability. Okay, so that's what you're going to be doing with this one. Okay, so every feature gets a say in determining which label should be assigned by the classifier. And then naive Bayes uses the frequency of each label in the training set. So that also is you know, another question is, so that one is more of a question of feature 2 in relation to CI. You see that? Probability of that one. You see that? You see how I wrote, you know, created that because I've said, well, what's the probability of, and actually I should generalize it, right? By saying K, right? So what is the probability of Fk given class I? And you have to find that, and that's basically some kind of account. And then finally, you're also going to say, well, what's the probability of just class I in the data set independently? So how many times was class 1 associated with a sample versus another sample in the training set? So it really comes down to these two parameters intuitively that we want to look at, okay? And so today we're just going to do a couple of examples, today and Wednesday. We're just going to do a couple of examples of how this works, okay? So what are probabilities? Well, we know this intuitively because we use this term. We use this actually every day, pretty much in everything that we do. What's the probability that if I eat these muffins, right, that I'm going to gain 5 pounds, right? So we do that every day, right? So we do that for everything. We just don't know it, but it's worked in our system. So what are probabilities? You know, something that, you know, it's a count out of something. Right, so that's 73% probability of something happening. One of the examples we're going to look at is from the field of natural language processing. We're going to basically have documents. It's actually because this is one of the most intuitive examples, right? So we're going to have documents, and we're going to try to classify these documents into categories, right? Let's say that you know, you're in some kind of a thing, and you want to find articles that are of interest to you, right? So they're going to categorize these articles into sports or sci-fi or, you know, politics, whatever it is that you're interested in, and then they're going to recommend it. So you're going to start with documents, but the documents have classes. And we know that documents are made up of words, right? So we know that words actually, a document by itself has no meaning. It's the words in it that determine, you know, what type of a document it is, right? So it's got words about sports, you know, etc. That's going to be important. Okay, so that's the idea there. So let's take an example, a more concrete example of naive Bayes, so that will motivate what we're doing. So let's say we're applying naive Bayes. We're applying naive Bayes to document classification. And we're not going to do any coding today, I don't think. We're just going to go over this framework and all the pieces. So let's say, what do we know about this document? Well, we have this problem, right? So document classification. So we need to define some things. First, one thing we're going to say is we have 100,000 documents. So these documents could be like stories, like let's say it's just books, right? So Huckleberry Finn, Dracula, you know, the classic books, right? So the specific size, we have 100,000 of those. Just for the sake of argument, keep things simple. Let's say we have, I know these documents have more words than this. I don't know how many words they have, 80,000 maybe. So let's just say 200,000. I just don't want to confuse things. So let's say there's 200 words per document. There's 200 words per document. This is important, right? Because every document is going to be represented by these words, but a lot of these words are not really important, like the word the. You know, how much value is there in the word the if all documents pretty much have the word the a lot? So we're going to skip the word the, get rid of it. But then we also want to get rid of infrequent words, right? So there's some infrequent words in there, right? You know, I don't know. That may not appear that much in documents. And so you can just ignore those words. And then we arrive at a subset of words that is the most frequent kind of important words, right? And we're just going to establish a vocabulary of, let's say, 50,000. And again, I'm just putting in some parameters in here. Not all of this is important, but you know. Now, if you remember, one of the things we were saying that we determine is to be able to make predictions, we kind of need these two things. Intuitively, we said, how many times do we see samples associated with classes? That's this one. And then we also said, well, if I have all these features, F1, F, you know, until Fn, let's say, what is the frequency that I see feature 3 or feature 1 associated with class I? You see that? So that's an important one. So that's the same. If we now look at it at the problem of documents here, let's say that we have the word run. So the word is run. That's a feature, right? Because what we're going to say now with the documents is we're going to use something called the bag of words approach. Not the most efficient, but it's a very long established approach to represent a document. So what that means is we have a document 1, and we have a document 2, we have a document 3, and so on, of the 100,000. But now they need to be represented as vectors, right? Just like always, it's always vectors, right? So we need to represent it as vectors. So what are the features? So what could be the features of a document to represent it? What do you guys think? The words in it, right? How would we map those in there? In that document. Yeah, exactly. That's actually a good way. So the count, basically, how many times that we see the word the in it? But the is probably not a good word to have. Instead, let's pick the word run, right? So now I'm going to say, I'm going to replace F5 with the word run itself, okay? And then you're saying, here we have a choice. Do we just say we saw that word once, at least once in the document? And so we would basically say 1. And then if F4, let's say it's the word space shuttle or space, and we never saw it in the document, it gets a 0. You see that? That's one way of mapping it. Another way is like you said, Noah. So if you have the word run and it appears 7 times, then we just plug in 7. If we don't see the word at all, 0. So it's a count, right? And so now the question is, if I have I've established a vocabulary of 50,000 words, and we're saying that each of those words is a feature, then what is the size of the features? How many features do you have? What is n? 50,000. Very good. Very good. What's the problem with that, though? That's a lot of features, right? And it's a sparse matrix because a lot of those features are going to be zeros. There's going to be very few that actually have values. A lot of them are going to be zeros. But do you guys get the idea? Okay, perfect. So this is actually the what is called, as I said, the bag of words approach. Okay, the bag of words approach. But it's an approach. It's a well-established approach, and that's the assumption for this. Okay, that we're doing this. For the next document, the word run may appear 2 times, and then 0. But then the word, whatever F4 is, might appear 3 times here and 1 time. And then everything else is just 0. Do you guys see that? This is how this works, okay? So it's important that you understand the context of what the data looks like. So now, given this information, we can say things like, you know, given the word run, okay? how many times does it appear in different documents. So we might say that in sports, in documents related to sports, it appears 12% of the time. And then in documents related to mystery novels, it appears 10% of the time. And then in aviation, it appears 2% of the time. Okay, so this is how we're trying to do this calculation, is we're trying to find these probabilities. Okay, we're trying to say these things about the world so that we can make predictions, and that's how naive Bayes works. But what's important is really using naive Bayes to understand the broader framework of probabilistic methods, okay, that become useful in other approaches. So as we said, naive Bayes is a baseline algorithm. It's usually the worst performance in terms of accuracy, F measure, precision, recall, but it's the fastest, right? So you guys saw that probably is very fast. So speed and memory is pretty efficient. We were able to get that. So how do we compute probability? So again, I go back to my initial intuition, right? So here we can calculate something about the probability of seeing the class associated with samples, but also each individual feature should determine something about the classification. So we need something where we have a probability of that feature given the class, right? So how many times did we see the word run in aviation? How many times, if those are the classes? Let's assume the classes are aviation, what was it, mystery novels, sports, I think, right? Those were the three. So what was the probability that we saw the word run given that it was sports? What is the probability that we saw the word run given that it was mystery novel? What is the probability that we saw the word run given that it was aviation? You guys see that? This probability, when it's something that depends on something else, it's called a conditional probability. Okay. So whenever so this should not be difficult, right? Because we just look at this. But if we have this, then we need to think a little bit more about it. What does that mean exactly? Conditional probability, right? And so because we are trying to predict for documents what class they belong to, right? So in terms of that, then what we need probably is what is the probability of what? So we want to predict classes for a document, right? So how would you write this conditional probability in terms of that? You know, we want to predict classes given documents. Or what is the probability that this document belongs to this class, right? So what is the probability of class given document? Do you see that? Where C is the class, D is the document. Got it? So this is called a conditional probability. And actually, it turns out that there's a guy, Bayes, who came up with something called Bayes' rule, which is basically an equation, really. It's pretty classic that allows you to compute this, right? It's going to show you how you can look at things because this involves a class, a document. So you can think of it this way. This involves a class, a document, and the combination of the class and the document. You see that? So it's like, you know, maybe the probability of the classes is important. Maybe the probability of the documents is important. Maybe the probability of the class given the document is important, the relationship. You see that? So Bayes then came up with something called the Bayes theorem or Bayes rule, which I wrote over here. And which is basically here, we're going to apply it to this problem of documents and classes. So the way that Bayes said is, we're going to write that the probability of a class given a document is actually the probability of the document given the class, okay, which we have in our data set. This is something that we actually have in our data set. We know for all the documents how often they were associated with a class because that's the training set, right? So it makes it, well, this is what we're trying to predict, but this is what we have organized, right? Every single row and a class, right? Remember, every single row is what? A document. And then we have their associated labels over here. Okay, so basically then, we can go ahead here. Yeah, so we can calculate this one, then base set, and we take that times the probability of the class, right? Times divided by the probability of the document. Okay, so this is actually Bayes' rule. Okay, and this is the formula, more or less, that we can implement for this. Okay, so you'll see there's how this works in a sec. So we compute the formula for all classes here. So what that means is that we're going to perform an argmax operation, and this is just a fancy way of saying the following: calculate the probability given the document for class 1. Let's say we have 3 classes, right? So same document, 3 classes. We use Bayes here to calculate some probabilities. Let's say 0.3, 0.2, 0.5. And argmax just says pick the highest. That's it. So then if this is the highest, the class should be C3. Does that make sense, guys? So you'll see this if you guys come across this term, a generalization of writing all of this is just to say that C is going to be argmax of the probability of Ci dk, right? So we look at the specific document and then we calculate for all the classes the probability, and then we just pick the highest one. But basically this, we write it out for all and then select the highest one. So it's the highest probability. So now the key thing is that Ph.D, right, is equal to the probability of DC times the probability of C divided by the probability of B, right? But now we're going to write this out for all the classes. So let's go ahead and do that. So if I do C1, C2, C3, I want to find the highest one. So this is going to be argmax probability of D C1 times the probability of C1 divided by probability of D. And then this is argmax probability of D C2 probability of C2 divided by the probability of D. And the last one is argmax probability of D C3 probability of C3 probability of D. Okay? So just by looking at this, what do you guys notice? Is there some kind of simplification that could be done here? Yeah, go ahead. Mm-hmm.
C1 and then C2.
What do you mean?
You have C1 equals R, and then you have document class 1. What if you were to group them together?
Yeah, no. No. So you have to follow the equation, right? So you have to follow, we're going to use Bayes' theorem here, this, right, to compute things. And we just have to do this computation for every single one of the classes. If we have 3 classes, then basically we write it out like this. So that this probability is the probability of seeing C1 in the document, like sports. How many times do we see documents that are sports? Sci-fi, aviation, that's that. PD is just a probability of the document itself. And then this one is the conditional, how many times do we see that document with that class, right? So what I was getting at is that if you look, PD here is the same for all of them. Do you see that? It's in the denominator. So because it's like saying this is always the number 4. So whatever all of this is always 4. So we can always just, if we multiply times, that, we can cancel, we can multiply all numbers times that and basically cancel that term. Do you see that? Because it's a common thing for all of them. So all computations are always going to be whatever they are plus this number. So they're all relative, so we can get rid of it. And this simplifies the equation to be even simpler, right? So just argmax probability of DC times probability of C. The denominator basically goes away. And that's really great because, it just makes the algorithm better. At the end of the day, we don't care about the actual value. We only care about the values in relation to the other values. And we pick the highest. So if this is 0.5 and this is 0.3 and this is 0.2, and then that PD for whatever reason is always 4, right? Then now it's 4.2, 4.3, 4.5. Same thing, right? Whether we select this one or that one, we always pick that as the highest. Got it? And so this is a nice way of simplifying this equation because, computationally it's expensive to have more terms, right? So we have that and we don't have to worry. What if calculating probability of D is really hard? It could be, right? In some other problems, that could be very difficult. But we don't need it, right? We don't need it. And so that's the great thing here. Okay, so now the other problem that we have is that we've simplified it, right? And we keep saying that we just need the document. But that's a very difficult thing to define. So what is the document? The document is only defined by the features here, right? So the words. So actually, we don't need the document. We need the feature vector that represents that document. Do you see that? That's how we need to represent it now. So here, we know that we have a document, the car is running, the car is going. We represent the document as a feature, as features, a bag of words. So now we're going to rewrite our formula from this approach to see argmax probability, and instead of D is made up of the individual words. So we're going to say X1, X2, X3, ... Xn. You see that? So that's basically what we've done now is we need, and if you think about it, it's exactly the same thing intuitively we had said over here. Exactly the same thing, right? The probability of the given feature associated with the class. But each document is made up of all these features. So these are the features here, right? So these are these features, F1, F2, the words themselves for this example. Okay, so I'll write it here even. So these are the words, features. Okay, so we have that. That's the interpretation of it. And then this is the probability of C. Sometimes this is referred to as the priori. These have terminology, so the priori. The interpretation of PC is how often does this class occur? You know, just the class itself. How often does it occur in the training set, right? And we should be able to calculate that easily. Okay, well, I'll show you in a sec how we can calculate those. Okay, so let's go ahead. So how do we get these frequencies? So basically, we're going to count them. So we need to count the frequencies in the data set. So we need to count. We need to count the frequencies in the data set. Okay. Now, keep in mind, one thing that's going to happen is, let's say we have two documents. The car is going fast. And we have another document. The fast car is going. These two have different meanings, right? The car is going fast could be an old, I don't know, 4-cylinder, car, right? The fast car is going implies this is some kind of a sports car, right? Something fast. You see that? So they have different meaning, but in the bag of words approach, we just plug in words, right? And if the words are car, going, fast, car, going, fast, 1, 1, 1, 1, 1, 1, right? Presence of the word. So what that means is that meaning is lost. Do you guys see that? Some meaning was lost in this sequence, right? So just be aware of that. It's not a perfect thing, certainly. So we got rid of order with the bag of words approach, and we need to make another assumption. We need to make an assumption that the words are actually independent. That's actually in Bayes. It's important. So we need to say that, and in machine learning, right, that the features are independent. Obviously, going and car are not totally independent, right? Cars go, right? That's the thing. So cars can be fast and slow, right? So there's some correlation there, but we're going to assume that these are independent. Okay, that doesn't really affect much, but now, so we had started with the formula then that to calculate the probability, we went from the document to class, right? But then we said, no, this actually needs to be probability of the actual features to class. But no, the problem is, how do you compute these? Well, if you assume that they're correlated, then you have a problem. But if you assume that they're independent, they're independent, so then I can just treat them as independent. Each feature is now a thing. So I can rewrite this as P x1 C times EX2 C times PX3 C dot PXN C. Do you see what I did here? So by saying that if we don't say that they're independent, then we have a problem. We can't do this. But if they are independent, we can break them up and just multiply them. Now, you may have asked, if I gave this task to you, go count this, you would have been very worried, right? How do I do that, right? But if I give you the task, the simplified task, just count this separately, individually, each one of the terms, you can actually do this. You see that? You can actually do that. Now in Weka, you just give it the data, now your base does it, right? In the Python script that we're going to work on Wednesday, we'll see, we can do it. But this is the idea, right? So the intuition is we can calculate these separately just by multiplying. Does this make sense, guys? Is this clear for everyone? All right, because this is actually then, now we have a nice thing. We just arrived at what we intuitively knew at the beginning, and we can count all of these. We know how to count for a feature given a class, and we know how to count for just a class. Okay, so that's what we're going to look at in a sec. Okay, so we've been able to write it, and just because just to look impressive here, I'm going to write it in math notation, but just think of it as code. So the probability of C, right, because this one is actually the original one, is PDC times PC, right? You remember, that's actually base rule once we remove the denominator. So that's this PC here. And then this sequence over here, because it's too long, we don't want to write it that long. We use a fancy math symbol for multiplication. This just means multiplication. And so we're going to say from I equal 1 to, what is it, n, right? For n, we take the probability of xi given the class. And this just means basically this exact same thing, the sequence of multiplications, but this is just written. So sometimes, you've probably seen like math somewhere and you saw this and you're like, oh my God, that's so inaccessible, right? But if you think about it, no, it's just this. And this just comes from that. And this is just a simple multiplication. You see a lot of the time, very fancy words. You see argmax and all that, and formulas, and it's actually pretty simple concepts. If you get into the code of it. All right, so now the question is, how do we compute these individual ones and this one, right? Because we need to be able to compute them. Now, there's another thing that needs to be addressed, and it's the fact that multiplications are not so efficient. Okay, so I'll talk about that in a sec, but I'm just saying right now, although we do this multiplication, theoretically speaking, there's actually a better implementation of it, right? And so we'll talk a little bit about it in a sec, but let's just finish up. So how do we compute these two, right? So that's really the idea. So the final question, we want to call it that, is how do we get these probabilities? How do we get these probabilities? Okay, so we want to get them. And basically, we just count from the data. So we need to find the probability of C for each class. So that's why it's CJ. And we also need to calculate the probability of each word. Think about it, of each word in the data set, right? Given each class also. Okay, so that's what we need to compute. These are the parameters that we need to provide. So here they are, without, pretty simple actually. So the first one, let's start with the probability of C. So how do you compute it? So just like we started before, Takes a numerator and a denominator, okay, to calculate it. So probability of class. The count here is going to be how many of the documents are in class J. You see that? That's it. So you just have to go into the data set, find all the documents that belong to class J. Okay. Once you do that, you have your numerator, and then the denominator is the count of all the documents. Which makes sense, right? Out of all the documents, how many belong to class J? Yeah, go ahead. It's a good question. In a large enough data set, it's probably not going to be a precise number. I see what you're saying, but probably, I mean, the theory is not to take it out. So leave it in. We'll see in the code actually that it does get added in, because you just don't know. I mean, I guess you wouldn't know. But yeah, it's a good question. It's interesting, actually. It's an interesting thought. So I like the idea. All right. So but this makes sense how you guys would compute this one. So you see it's simple, right? Don't you think? Simple? Huh? Yeah, exactly. All right, good. Yeah, and then the other one. So another, actually, maybe I wrote it like this because I want it to be very clear, but a more summarized way could be docs per CJ divided by n documents. To be consistent. The same thing, right? So same equation. All right, and then the next one, which might seem a lot more complex, it's not. It's actually very similar, very intuitive. This is going to be the probability of WI given CJ, right? So you write it over here. That's the probability of WI CJ. So I'm going to write it out again, big words here. So numerator is going to be the count of how many times WI occurs in documents of class CJ. Do you see that? So the count, basically, you're going to count how many times you see the word WI in documents of class CJ. So find all the documents that are class CJ and then look for that word in it and just count how many times you see it. Divided by the total number of words, in documents of class CJ. So in all of them, you're looking for just documents of that class, but in one, you look at all the words. And then in the other one, you just look for the specific word and count how many times you see it. Is that clear, guys? Questions? No? Yeah, and so as you can see, this is another one that's pretty straightforward, actually, and that's all you need in this scenario to calculate the probabilities. So now, a lot of this, when you're doing these things is, calculating these probabilities, the frequencies of seeing all these documents, etc. Okay. Now, one issue with a lot of these is that you always want to do probably +1. The reason for this is, let's say that you get probabilities that are so small, right, that they would give you problems, right? By having that +1, you have, right, and it doesn't end up being a division by 0, etc. So you always do this little +1 thing. Okay, questions? Did this make sense? That's it. That's the general framework of naive Bayes. What you do is you add it by default in the equation. It's always there just in case, because it's going to be in both sides, right? And just in case, so you don't end up with a 0 division. Got it? All right. So now let's go back to, we do have one little problem. So if we go over here, remember the multiplication, right? This multiplication is actually problematic because, first of all, these are probabilities already, right? All of these are going to be values between 0 and 1. You see that 0.8, 0.20, 0.30, right? If you have a lot, and you have a lot of words in a document, correct? Lots of words, don't you think? So what's the problem, you might say? Well, the problem is the framework is good and all, but you're going to end up probably with 0.05 times 0.03 times 0.50 times 0.40 and so on. Do you see that? What's the problem with this? Yeah. And what happens when you multiply two values that are really small together? I see what you're saying. So, and what does that have? What does that mean? When you half something every time? Smaller and smaller, right? Good. Yeah, good. All right. So what's going to happen? So if I take an example, 0.001 times 0.001, this actually is going to be 0.000001. You see it, which is, you were correct in what you said, but this is a very big problem in machine learning. Happens a lot because you're multiplying things. It happens in neural networks too. In neural networks are frameworks where you have a whole bunch of inputs, you learn weights to associate those features and arrive at something. We'll see this later, but I want you to understand this problem. This is a neural net, right? Basically, you have x1, x2, x3, the inputs, and then you're going to say something about the output. You have to estimate W1, W2, W3, which are the values that you multiply times x to get y. So this ultimately in a neural net is W1 times x1 plus W2 plus x2 plus W3 x3. Do you see that? Oh, x3. This together, this together, this together to assign one. You guys see that? So obviously we haven't even started neural networks. So we'll come back to this idea. But what I want you to see is that every time that you're manipulating these weights over and over and over and over, you're multiplying them also by something. And again, when you start getting into values that are really small like this, they just become smaller and smaller and smaller and smaller and smaller and smaller. right? And so this is a very common problem in machine learning. Sometimes this is called a vanishing gradients. When these values become so small, they might as well be zero. You know what I mean? You've gotten no meaning. And this is especially true in sequence models. But in naive Bayes right now, we have potentially, what was the size of that vocabulary? 50,000 words. Every one of those we were going to multiply, and every one of those is a probability. You see the great problem that we have. So, but there's actually a better solution that is equivalent. Instead of multiplying things, as it turns out with probabilities, because at the end of the day, all we're doing, remember, all we're doing, just like we did before here, just like we did here, right? Where it didn't matter if it was +4 or not, because at the end of the day, we just picked the highest one. We're still doing the same thing here. And so we're just going to rewrite the notation a little bit from this. So this is how it should be, right? Probability times probability, times probability, right? That's basically this, right? So this here is that multiplication. So it's a sequence like this, ... Instead, this can be rewritten as log of probability plus log of probability plus log of probability plus ... This is a nice solution because the results are still going to be proportional to what they were before, but now we don't have that issue. And so we write the multiplication like that. So it's a sum instead of a multiplication, as long as we use the log. This is just a math thing. Sure you've seen somewhere in your algebra classes. And so this is the idea, okay? It's just a kind of an algebra trick. It just holds. And this is actually important because in the code that we're going to write, we're not actually going to write the multiplication version, but we're going to write the log version. So if I don't tell you this, you would be very surprised when you look at the code, okay? But if hopefully you understand that this is where it's coming from. Remember that these are the feature I, class, feature 1, I guess, feature 2 class, and so on. And remember, at the end, there's the probability of just a class, right? Because if we go to the equation over here, right, remember, it's all the multiplications, and then finally, the probability of the class is really important, okay? Okay, so that one too, because it's part of it as a multiplication, would also get its log as well and be added together. So they're all added instead of multiplied. Is this concept clear, guys? Yeah? No questions? All right. So anyway, that's the idea, right? So this is the framework. So keep in mind, when we look at the Python script, it will look like this. We will have those logs in. The other thing that we're going to do is, instead of counting, we can use another way of estimating the probability. So the probability before, we just did, count, right? The counts and counts, right? We did that here, right? These counts. As we were looking at the problem of documents, predicting the class of a document, it's more of a traditional. But let's say that you want to apply it to the iris data set, right? It may not be as straightforward to compute that with the iris data set, right? Because it's actual values like 0.60, 0.75, whatever it is with iris. So, but there's another way of estimating the probability based on the Gaussian function. So based on the Gaussian function, so what's the Gaussian function? You guys took a statistics course, correct? All right. So I'm sure you saw this. And so we're going to use that. It's called a probability density function. And it's basically a little function that allows us to estimate a probability, just like we did with the counts, but now in terms of just the distribution of the data for that given feature. Got it? So instead of calculating how many times we see this feature in the document, instead, it's more like what's the mean and the standard deviation of that feature, because the words were features, but now we look at a specific feature, like in iris data set, we have 4 features, right? So we look at one. If we calculate the mean and the standard deviation of the whole column, F3, we know a mean and a standard deviation, correct? Again, the example of predicting if people are going to buy something or not. Look at their parameters, right? Height. Okay, so we've got 100,000 people. They all have different heights, but can you take the mean and the standard deviation of the height for the entire group? Yes, right? Because that's, let's say F3, you have all the heights, you get the mean, you get the standard deviation. And then with those, you can model them in a function. And when you get a new feature, it'll tell you what's the probability that this feature came from this data set. It's, it's another way of saying if the person is 6'6", what's the probability that they are from that? Probably very low, right? But if it's, 6'1", right, that might be more in line with the population. Does that make sense, guys? That's how we estimate the probabilities in a more generic way. So what we want to do is we want to generalize our initial framework of PW I CJ, right? So we want to generalize this, okay, to be probability that Fi, given CJ. Okay, so then we need to find a generic way of saying this that would work for us. And that's going to be a function called the Gaussian. Okay, that will take F and C. Right, so the probability of, I should have written this as probability of F given C. Okay, now remember, what is this function Gaussian? That's just from your stats course, the normal distribution. You guys remember that? This normal distribution is a function, right? So usually it's determined by the mean. And then here you have something like the variance, right? So the distance from the mean in every direction. So that's usually called a standard deviation, or a square of that is the variance. So mean and variance. Got it? So if we have for a feature F1, F2, F3, now we can just look at all the data for that feature and estimate a mean and estimate a variance. With those 2 parameters and the Gaussian function, we can say a lot about the data. Whenever we get a new sample, basically what we're doing is we're plugging that sample here or here or here, right? So if it's a really tall person, probably they fall kind of not so close to the mean. So the probability is going to reflect that. It's going to say, well, this person, there's a 0.20 probability that they come from that distribution because they're kind of outside. But if it's 6'1" or 6, it's closer to the mean. And that applies to any single feature that you can think of. You can do the same trick. So then this probability would be like 0.8. You see that? And so just like before we were calculating probabilities like that, now we are calculating probabilities like this. Okay. Questions about this idea? No? All right, so remember, for every feature you calculate for F1, let's say iris, right? Iris is F1, F2, F3, F4, right? So for F1, mean and standard deviation. For F2, mean and standard deviation. F3, mean and standard deviation. F4, mean and standard deviation, okay? And then once you have that, you can basically create this function that says, what's the probability? Well, I have a function, it's the Gaussian. I'm gonna plug in my feature. Oh, sorry. I'm gonna plug in my feature, my mean, and variance for that feature. Let's say we're talking about F3, right? And then I get a new 3, but a new one. This is gonna return the probability of it. Just like before we were doing counts, now we do it this way. Got it? Is this a concept you guys get? Any questions? Yeah. All right, so then what does this look like? So the function can be represented as the chart looks like this, right? So the graph or the drawing or whatever you want to call it looks like this. Mean, standard deviation, right? So we need to find these parameters. Okay, we need to find them. Now this function, or sorry, this little thing here, this shape looks like this as a function. 1, 2 pi. This is the standard deviation, right? So this is one of the parameters. So maybe I'll write the parameters later in different color, times the exponential of the x is the input minus the mean squared divided by 2 variance squared. This thing, this shape is written like that. Because we can't like draw this, right? We can't draw this in a code, in a program, and oh, does it fall here or there? What we can write is this, and then when we plug it in here, it's going to give us the value. Got it? So what's one important thing to notice here is the parameters that are inputs, right? So the parameters that are inputs are this one, right? That's the standard deviation. Variance is its squared, so this is the standard deviation. Another one is x. The new feature that we're looking at, the mean, right? That's another one. And here's standard deviation. Again, so that's why mean, variance, and x, that's these 3. So this one and this one is variance. This one is mean. This one is x. Got it? And then the rest is the equation. We plug that in and we should get our outcome. This exponential, this thing is just e to the x, if you remember from your algebra classes. That's just that. Okay? Questions? No? Okay, so that's basically the idea. And then the last part is, how do you calculate the mean and the standard deviation? We will actually do this in NumPy pretty easily, but mean x1 plus x2 plus x3, right, divided by 3. That's the mean. Okay. The variance should be, maybe I'll do an example here. So 6 plus 11 plus 7 divided by 3 is 24 divided by 3, which is okay. And then the variance should be variance should be 1 divided by n. This symbol just means the sum. Sum from I equal 1 to n of xi, right? All the samples minus the mean squared. Remember, for the data in the training set, we looked at all the data and got mean and standard deviation. These xi's are from the test set. Okay? The test set. We're just comparing. We have a new person, new client. How tall are they? Well, how does that compare to the distribution? How is their income? How does that compare to their distribution, and so on? Okay, so this is a general framework that is extremely powerful for calculating probabilities. And so hopefully. And so now that we have this, what we have to do computationally, now this is more how we're going to do this in NumPy on, we're going to do this, and I ran out of slides, so I'm going to erase this. All of this is in bright space, so you can just put it. But so the last part, and I'll close with this today, is we need to do this computationally for our code, right? We're going to do this on the Jupyter Notebook on Wednesday. So we need, let's say for the iris data set, right? So iris, we have, the classes are Virginica, Setosa, and Versicolor, right? Those are the 3 classes. So basically we need 0, 1, 2. We're going to create a matrix for each class. And we're going to use the class as a type of index to get the value that we need. Then it's got F1, F2, F3, F4. That's just the iris data set. I like this data set for this problem because it allows us to see it completely for iris, right? So I've got these, and then for every feature and for every class, I'm going to calculate the mean. Do you guys see that? And then I'm going to have this available so that every time that I get a new sample, I can compute their probability, given that last function that I showed you. Where was it? Yeah, this function. Okay, so a lot of these elements are what we're going to do in the code on Wednesday. The other thing that you need is this is the means. You also need the same thing, but for the variance. So 0, 1, 2. Oops. Features are F1, F2, F3, F4. Okay, so variance, 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 variance. We're going to compute all of those. And then once we have them and the equation, we can proceed to calculate the probability for everything and then do the computation. Is this clear? Yeah. As I said, this is important because this is, these little things you'll see in the code and they'll be like, what is that? So yeah, no questions. All right. All right. So that's basically, I think, all of it. Let me just make sure I didn't miss anything. Oh, yeah. So when one thing, because you know, it's just for completion, I guess, when we looked at the generic framework for a class, probability of D CI times probability of CI, we're just going to give these names. Okay, so the names are for this one and that term. So this is usually referred to as the priori term, and this one is referred to as the likelihood. So just be aware of that. Okay, likelihood. Okay. Yeah, so that's basically it. So we are done with the theory of naive Bayes. Now, what's really important about this is this framework, the Bayes rule, naive, you know, Bayes theorem or Bayes rule will come again because I'm doing this sequence, right? I've started with naive Bayes, then hidden Markov models, and, you know, some additional sequence things. And so hopefully this is a base, a foundation for you guys to understand the other ones a little bit better, right? Because they will have some aspects that are similar. You guys understand? It all builds off each other, yes. Correct. All right, so I'm gonna go ahead at this time and I'm gonna stop the recording.